There.
Uh, yes, good evening, Prathadan.
Yes,
How are
yes.
you?
Good evening, good evening, good evening. Nice to see you after quite some.
No, no, I think same
Actually,
here. It is good.
back-to-back sessions are
Yes,
going. Sessions are going back to back. The previous session just got over, and we are joining immediately to your session now.
no, no,
The
sure. I
sessions are
think
from six
please take
to
your
seven
time.
thirty, and then 6 to 7:30 and 7:30 to 9. These are the two sessions going
I
on.
agree.
So that session just got
Okay,
over. The question answer and
wonderful.
etc. So so others are joining. How is the winter
It
there
must be
in
very.
Jodhpur?
Yes, it is. The winter has like started in I think 15 days back, and now it is. You can see that I am wearing jacket.
I can see
It's
that.
at,
Okay.
yes.
Yes, 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 yes.
Yeah, so it is going to peak like December, and it would be, I think, night temperature would be around 1 degree or around so. Yes.
Uh, uh, yeah. So 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 yeah. So, but the temperature in Jodhpur is uh, similar to Delhi.
Yes, it is similar to them. Winter would be slightly harsh here in Jodhpur, maybe
Hmm,
difference of 2-3 degrees. Yes.
sure.
Temperature would be lower in Jodhpur.
Hmm, hmm, hmm.
How about in your place? It is, I assume it is pleasant. Yes.
I mean, I would put it this way that Kolkata is less harsher than Delhi, and
Okay.
and but Bolpur is 2 degree harsher both in summer and winter.
Oh,
I mean, in a
oh,
sense, in a sense, it is
okay.
pleasant. It is pleasant. In a sense, it is pleasant
Okay.
because
Yes,
winter in India is only for 2 months.
I agree. I agree.
Yeah.
So, good evening,
Good evening.
Dr. Shuril Bisha. I am Pranav Kanti Rai, co-coordinator of the program.
Good evening.
So, should we start the?
Yes, please.
So, before that, let me introduce to our participants about the Dr. Shuril Bisha. So, Dr. Shuril Bisha completed his PhD at Indian Institute of Technology, Delhi. After completing his PhD, he was associated with McGill University, Canada, as a postdoctoral research fellow, where he specialized in space robotics. Later, he joined Indian Institute of Information Technology, Hyderabad, as a research assistant professor. He has been with Indian Institute of Technology, Jodhpur, since 2015 and currently serves as a professor in the Department of Mechanical Engineering. Dr. Shah established the robotics laboratory in Mechanical Engineering department at IIT Jodhpur and coordinated the interdisciplinary research platform on robotics and mobility system at IIT Jodhpur. He is an active researcher in dynamics, motion planning, and control of robotics with specific focus on space robotics. He has a large number of research publications in reputed journal and conference proceedings. His work on modular framework for tree-type robotic system has been published as a book by Springer, Netherlands. Dr. Shah is actively engaged in research, teaching, and technology development. As an outreach initiative, he has contributed to the development of a free recursive dynamic simulator for modeling and analyzing the complex robotic and multi-body system. So now, Dr. Shah, the session is yours. You may continue.
Thank you. Should I switch off my video in case there are some bandwidth issues? Like, is
Okay,
it
okay,
okay?
no problem. Oh,
Sure,
it is okay, no problem, no problem.
sure. Yes. So before I begin, just wanted to confirm that my screen is visible and my voice is clear.
Yeah. Screen is visible and voice is also clear.
Fine. So thank you for kind introduction and opportunity to deliver this talk. I also welcome all the participants who have joined this FDP program. And today I will be talking about robotics shaping the future of process automation and quality assurance. And you will appreciate that this topic is of utmost importance, considering today we are moving towards smart manufacturing, where intelligent machines and data-driven manufacturing will play important role. I'll try to talk about uh, uh, use of robots in achieving automation and quality assurance as a part of this presentation. And I'll also try to highlight some of the takeaways for we as a teachers in time to come. So before I move, I thought I'll briefly talk about what research that I have been doing at IIT Jodhpur, and I'll touch upon some of the topics as I move forward. So I work at IIT Jodhpur in the Department of Mechanical Engineering, and my major research domain is robotics, where I have been focusing on motion planning and control, robot mechanism design, vision-based control, and computational dynamics. And I have been majorly focusing on two application areas, space robotics and mobile and compliant robots. As far as space robotics is concerned, I'll try to take some of the research issues that we have been solving in third part of this presentation. So while given this opportunity, I was thinking how to plan this presentation, and I thought of dividing into mainly three parts. Because when you try to talk about robot for automation and improving quality assurance, it's very important to understand that how field of robotics has evolved and what are different applications and what do we call robot today or what are its attributes. And that would be first part of my presentation. And then I'll briefly touch upon, even though I'm not expert in quality assurance, I'll try to touch upon robotic process automation and quality enhancement. And focus will be on emphasizing the fact that when we combine automation with robotics, there is inbuilt quality enhancement due to some of the features which are being added by robots itself. And in third part, I'll talk about autonomous on-orbit services using space robot. And I'll talk about some of the research work that we have done. So I'll begin with evolution of robot, and I would like to start with this image, which is nothing but imagination of Leonardo da Vinci, who was scientist, artist, and he visualized robot as something which would be like a human, which would be using pulley, gears, belt drives. And this was visualized by him or conceptualized by him in 1495. And you may realize that there are a lot of interesting work which were being done in past. They got lost. Similarly, this work was also got lost and it was rediscovered in 1950. And now inner working is displayed in a museum in Berlin. Now, later, if we move further, William Goodwin in 1867 came up with design of mechanical horse. Again, you can see a lot of gears, pulleys, belts, and that was the initial thought process of robot where they'll imitate either human or animal mammal. However, the word robot became popular in 1921 to Rossum's Universal Robot by Karel Capek, where there were characters such as robot, and this played important role in increasing the publicity of world robot. However, it became very popular in 1950, where Isaac Asimov wrote a fiction called I, Robot. and also gave 3 laws of robotics. We may not get into the 3 laws of robotics, however, we'll try to see that how the robots or field of robotics have evolved, and various researchers during this time started working in the area of robotics. However, if you look at the initial thought process of Leonardo da Vinci or William Goodwin, they conceived robot as a mammal or a human or structure similar to mammal and human. However, the first robot which was being built or conceived and which was being applied for industrial usage was like a human arm. So it neither mimicked entire human, but it just mimicked human arm. And the first robot was created by Unimation Technology, and it was known as Unimet robot in 1961. And I would like to emphasize one aspect, that the first robot, in contrast to human arm, when we have all revolute type joints, such as spherical joint, uh, or revolute joint or spherical wrist, the first industrial robot was having a prismatic joint. Now we appreciate the fact that prismatic joint requires regular routine maintenance. All of us here are using vehicle which has IC engine which needs to be lubricated regularly, and dust particle may get accumulated and then you may also require to do servicing. On the other hand, the door hinges we never require to lubricate, hardly we lubricate unless it start making noises. However, the first robot was having prismatic joint because in 1961 the computational capability that we were having were not sufficient to solve complex mechanics associated with robot, or more specifically kinematics associated with robotics, and intentionally prismatic joint was introduced in the Unimet robot, which was created in 1961. And later, now most of the industrial robot that we see, which would replicate human arm, which would be having 6 degrees of freedom. And here is one such robot, which is Cincinnati Milacron T3 robot, which is having all revolute joint, because with advent of computational resource, now we are having good capability to solve kinematics problem related to robotics. So this was in 1961 when first robot was being built, and then subsequently we find a lot of industrial robot in industries. And I would like to emphasize that the original notion of robot was manipulator arm used in factory automation. However, since 1961, there has been a lot of progress in the field of robotics, and its application and usage has penetrated in various fields. And I would briefly like to highlight some of the innovation which were being done subsequently from 1961. I would like to highlight this robot which was being built by Stanford University, named Shaky in 1969. And the unique feature of this robot was it was first fully autonomous robot. It had camera, rangefinder, bump detector, onboard logic. And I would like to highlight the year because I always tell students that, say, if you are building something in your robotics lab, hobby club, then at least you should build something which is better than Shaky, which was being built in 1969. Moving forward, I thought of introducing some of the work which is being subsequently, which will play a very important role in time to come, and which also aligned with the dream of William Goodwin, who gave conceptual design of mechanical horse. So researcher named Mark Rebert at Carnegie Mellon University started working on legged robots. And in fact, he started with one-legged hopping robot just to understand how robots balance itself. And I would like to show some of the videos. So here you can see that they have done very systematic studies on one-legged robot. It is kangaroo-like hopping robot, which is hopping on one leg. There is well-defined environment. You can see there are square blocks on the grounds. So it is working in very well-defined environment. Subsequently, they introduced 2 legs. And I would like to go back that all this work were being done from the duration 1976 to 1991. And you can see they also tried out high-speed locomotion with bipedal. They have tried out obstacle avoidance, that this two-legged robot was able to jump over obstacle, and it was also able to do somersault. And then they have done a lot of studies, tests, and yes, that this were very interesting set of research which was being done by Mark Rebert and his group. And subsequently, they also extended this to four-legged robot, and they came up with interesting set of results which are still being used by researchers working in the area of robotics. They have tried out different gaits of legged robots. Yes. So this was very interesting set of activity which was taken up after evolution of industrial robot as a human arm, or which is similar to human arm. Now moving forward, I'll come back to today. And when I say today, it may be little 2-3 years ago or 3-4 years ago. This video is not the most recent video by Boston Dynamics. There has been a lot of interesting work which is being done subsequently, but there is a link between the previous video and this video, that the researcher who did work at CMU and MIT subsequently started his company called Boston Dynamics, which was being taken by Google, Hyundai, and then various, and it has created very interesting set of robots which are going to play important role in time to come in manufacturing as well as in automation and quality assurance. So I thought of showing this one video which summarizes the capability that we have achieved today, and lot more than what I am showing is being achieved, because this video is little old, but still it will give some idea of what we have achieved in last few years. So now what you may see, that these robots are not working in very well-defined environment. There are no markers on the ground. These robots have come outside the laboratory, and then they have capability to move on snowy terrain, jump from one obstacle to another obstacle without any marker on the ground. They have better stability than the robots which were being shown earlier. They can be ready very soon in working or replacing human in various workplaces, warehouses. They have capability to stand on its own, learn from its mistakes. Here is very interesting robot which is known as Spot Mini. It is a four-legged robot carrying a manipulator, and it is opening a door based on the vision sensor. There is a robot, again the same robot which is being used in kitchen for object manipulation. It has very wonderful ability to climb stairs, and you can see how smoothly it is climbing stairs. It can rebalance itself, and now there are a lot of companies, and even in India, people have started building and making four-legged robot, and you will see that in time to come, that will play a very important role in industry automation. Here is another interesting robot which is having wheel-leg combination. So it is having two legs, however, the legs are attached with wheel at the end, which will essentially give us speed, better stability, and ability to lift higher object. And it employs intricate control strategy in achieving capability that it has. Here you can see that it is doing endpoint control. This is another famous big dog robot, which you may see that it is negotiating uneven terrain. It is also taking external disturbances in the form of kick, which was being given a slopy terrain. It is able to negotiate snow, even oily terrain. And such robots are going to play an important role in time to come, especially in defense application. You can see that it is able to negotiate terrain such as snow. This is very interesting set of robot I thought of showing because any idea that you may create it may not require a lot of money, but it requires creativity, and you can see that it's a very small robot, not very costly, but you can see that it can climb higher heights. And for creating something amazing, you require what is creativity rather than money, and that's where we need to encourage our students to focus on. So I thought of showing some of the development, and now there are many more interesting robots with better capabilities have come up, and you may find these robots on YouTube. But I just wanted to show a journey of academician who started his career at CMU and MIT and then spent 20 years of his research and subsequently venture into product development and now creating best of the robot in world. And if he can do, then many of us can also think of taking this journey in time to come. So with this brief introduction of how advancement of robot has happened from industrial robot to diversity of robot that we are having, I would also like to emphasize that now application of robots are not limited to industrial environment, such as automobile industry, where you will find thousands of robots in assembly line. There are many applications which have come up, and I thought it is very important to look at this application because automation is not only limited to industry. And I'll focus on robots combined with automation will bring in inbuilt quality assurance, and that can be seen in various field and aspect. And that's why I thought of showing some of the application which would give you some idea of broad perspective or application domain that one will have to deal with as far as robotics is concerned. So robots are increasingly being used in industry automation, where you can see that industrial robots, these are arm types robots which are being used in automobile industry. There's an assembly line and major of the work are being done in automated manner, while set of thousands of robots which are operating in environment. Here is a warehouse environment scenario where robot will play increasing role, and there are many warehouses where this kind of robots are being deployed. Robots can also be used in emergency and hazardous environments, as it can be seen here, where robots can play important role and replace human in environment which could be dangerous to human. Robots can also be useful for surveillance and exploration, and these are different kinds of robot. Here you can see a mobile robot carrying a manipulator and doing some kind of inspection of wall or what's there on the other side of the wall. Second image you will see bird type of robot. Third image you see quadcopter. The fourth image shows NASA Mars rover, and fifth image is nothing but six-legged underwater robot. And it can be used increasingly in surveillance and exploration application in time to come. In fact, they are being used today as well. Robots can also be used for locomotion. For example, Amazon has long time ago started its priority service based on drone in USA. And here is the big dog. We already seen the video, which can be used for locomotion purpose, and it is having a defense application. There are also robots which can be used. For example, the first robot created by Sony, second by Honda, and these are mainly being projected as an entertainment robot, even though they have been doing really in-depth scientific research. However, these robots are being demonstrated by Sony and Honda at various places. And the third image, you see that there is an industrial robot, arm type robot, which is carrying a human. And you can design interesting motion profile for end of the robot, which will create certain acceleration profile and create thrill to the human rider which are sitting on the robot. Moving forward, agricultural industries, there is shortage of worker, and there are a lot of applications. There are a lot of robotic applications which are being developed, and there are large machines. However, everyone or every farmer having those large machines would be challenging. On the other hand, one can always have robotic solutions which are cheaper, smaller, simpler, and can be used even by farmers who are not very rich. There are also applications where robots are being used for construction application, or I would say 3D printing of houses. And here you can see the images where robots are being used in construction application. Another interesting area where robots are being used is for simulators. So what you may see in this image is there are two simulators. There is a vehicle simulator in the first image and airplane simulator in the second image of Lufthansa. And at the bottom, you will see that there are 6 parallel legs. And these 6 parallel legs are nothing but it is very popularly known as parallel robot. So pilot would be sitting on this platform and it would be seeing a virtual environment in front of him or her. And this parallel robot will create motion profile which will mimic actual aeroplane as if pilot is driving the aeroplane. In fact, Delhi has also started doing license giving procedure based on this simulator, where you would be actually driving this simulator and then they'll be giving you the license. There are robots which can be used for certain rescue application. Specifically, the second image shows a robot named Packpok, which was being used during 9/11. There are robots which are being used for surgical application, and even in my city, Jodhpur, a few years back, the AIMS Jodhpur very proudly mentioned that they have completed 1,000 robotic surgery. In fact, 5-6 years back, and by this time they must have done more than 5,000 robotic surgery in city of Jodhpur. And there would be also micro nano robot, and there is a lot of research which is ongoing, which will get into human body and then can do amazing repair and amazing stuff in time to come, which will certainly give longevity to us in time to come. There are also other category of robots which are known as exoskeleton. They are like wearable robot. So in first image, you can see that there is a wearable robot which can be wear by the human worker, and they'll uplift the capability of human worker in doing work. One can also use this exoskeleton device for gaming and other purposes. And here you can see that the person with disability is being enabled by exoskeleton. So these are all actuated exoskeleton, the one which are there in the first and third image, and has given capability for or capability to human to walk. There are also a lot of assistive robots which are going to be used in time to come in homes, in shop floor, laboratories, and various other places. And you may find this vacuum cleaning robot now very cheaply available on Flipkart, Amazon. Can easily purchase and it will do a lot of cleaning stuff easily. And its quality and precision has also improved over the time. And it is going to play important role, this kind of robot, in service industry in time to come. There's also another use case where robots are being used to teleoperate. There may be scenarios such as nuclear plant or many other applications where teleoperation will play important role, where a human will teleoperate the robot. So that's also another interesting area. And haptics is nothing but sense of touch. And robots are being deployed for teleoperation with help of exoskeleton, which we have seen in the previous slide. I thought of showing this very simple video that this video is also old and there's a lot of progress which is being done subsequently, but it also gives us idea that today the field of robotics has penetrated workplaces, shop floors in many developed countries, and increasingly it will also uh, uh, come into picture in various industrial environment in Indian economic scenario. So I'll quickly take you through this video where there is a simple mobile robot where there is a workplace environment where the boss has entered into this robot and he is interacting with employee and then getting update about the things. And such robots are very cheaply available today and they are also being deployed. Yes. So telepresence through robot would be very important and will play important role in time to come. Yes, I'll fast forward and I'll summarize the first part or part of the first part, and I wanted to emphasize one aspect that the notion of what qualifies as a robot has changed greatly over the years. So I have long time ago I stopped giving laws of robotics given by Asimov because those laws have evolved over the time, and then even robot itself has evolved, and now you may find different kinds of robots which are being used in different applications. And it's very important to revisit the definition of robot or deciding attributes of the robot, and that would be the next part that I would be focusing before we get into the main presentation of today's talk. So it's very important to understand what are attributes of robot, what does it do, how do we define the robot. And I would like to emphasize that the primary work that robot does is, first part is it gathers information about its environment, obstacle around it in the form of sensing. It gathers this information. The next part is it tries to locate this information and try to process this information to make subsequent decision. And the second part is thinking. So it senses the information, it performs thinking, and whatever action that it takes, it is based on this sensing and thinking. And I would like to emphasize that if we try to improve the sensing and thinking ability, obviously quality of action that it will take or the subsequence of action or consequence of action that robot has taken will also improve. So first part is sensing, second part is thinking, and the third part is acting on the environment. And these are the main attributes of a robot. So any robot that you think of, it senses the information, it processes the information, think about it, and then it come up with action. And it apply and then again look at what is the consequence of the action which is being taken by the robot. So how do we define a robot? So to be called a robot, an entity must be a machine which is capable of doing some real work. That's the primary requirement. And obviously, as it performs sensing and then make any decision based on the thinking and whatever action that it takes on the environment, it again get feedback in terms of sensing. So it should be able to work in closed loop fashion under computer control. Therefore, a robot is a mechatronic system and at the heart of which is feedback control. That's what I would like to, and control has taken different role. Today, control, when I talk about control, it may not be the physical control, it would be data-driven control. It could be stochastic or predictive control. It could even be learning-based control such as reinforcement learning. However, that is going to be heart of the robot and it would be surrounded by sensing, which is very important. Obviously, you will have software, electronics, and mechanics. And whatever action that it takes, it is purely based on the feedback control law, which essentially allow autonomy, and it also allows it to perform in unstructured environment, which may have a lot of obstacle, clutter, dynamic obstacle, and even human being. So before I conclude the first part, and learning is going to play important role, it is playing and it is going to play important role in achieving autonomy and performance in unstructured environment. So I thought of showing this one slide before I conclude the first part of my presentation and eventually move to the second part. So I would like to again take you back to the conceptualization of Leonardo da Vinci. So he thought of a robot as a humanoid or something like human, which would be having all capabilities similar to human in 14th century. And when I talk about what is ultimate robotic system, obviously I would like to go back to the idea of Leonardo da Vinci, and then it should have mechanics in the form of hands, arms, and legs. It would have sensors such as camera, force, and touch. It would have brain in the form of computer, and it incorporate feedback control. That means all the actions which are being taken by the robot, it's based on the sensed entity from the environment. So I would like to show you one such humanoid robot. I talked about humanoid by Honda. This is also old video. My apology for showing old videos for this presentation, but these are still relevant. And I thought of showing. So this is a video released a few years back by Honda, where you can see that this humanoid is able to navigate in unstructured, unknown environment. It is able to avoid obstacle in the form of human, and so it has a very interesting set of capability. Now let's try to have a look at the walk of the humanoid, the way it is walking. So maybe there is a question for participant. So do you have any observation? Uh, any observation about the way this humanoid is walking? Whether participants have any observation? I may keep this video running, and if you can just observe the way this robot is walking, do you have any comments to make? Whether it is very conservative walk? Yes.
Yeah. Regarding the motion,
Yes. Whether someone would like to comment? So, yes, what I see that this walk is very conservative. In a way, this humanoid is bending its knee and walking. Now, let's imagine, let's say if you have to bend your knee and walk for a kilometer, then at least you have to be on your bed for one day, because it's very energy consuming way of walking. Just imagine bending your knee and walking for a kilometer, and your all energy will be drained out. And hence, if you carefully see this walk, the robot is bending its knee and walking, and which obviously is energy consuming task. Now let's look at, so robot today consume lot of energy, and we need robots which are natural, consume less energy. There are limitations as far as actuation and sensing is concerned. If you can cross this threshold, so sensing, actuation, and energy, obviously we have made a lot of mark as far as AI algorithms is concerned, but once we cross this threshold of getting highly responsive sensor, actuator, and sensor, we may be able to achieve much in time to come. Nevertheless, I would like to show one of the video, and then before I move to the next phase of this presentation, I would like to ask one question to all the participants. Yes, so if you can please carefully look at this video. I'll rerun this video. So don't you think that this robot is walking like a casual college goer, and it is walking in much better manner than the Honda robot which I have shown? Any guess about how many actuator the second robot uses? Yes. Any participant would like to comment? The second work is by Steve Collins and Andy Roina. Uh, and any guess that you would like to make on number of actuators which are being used by the second robot? Let's assume that the Honda Asimo robot is using in the range of 30 to 35 motors. And how about the second robot? Any guess? Any number that you would like to make? I hope participants are having access to uh, use their mic and answer the questions.
Regarding the second motor, I would say
Yes.
that the number of actuators will depend on the joints. Is it right?
Yes. So what I'm looking forward to is just to know that a wild guess. What do you think? Because what I have summarized, and you might have also appreciated that second robot is having more natural walk. It is more natural walk. It is not bending its knee and walking.
Yeah. It is not
And
pain.
if it is having natural walk, and if Honda Asimo is having more than 35 motors, what is your guess? How many actuators the second robot is using, which is actually having more natural walk than the Asimo created by Honda?
Second motor has been lesser number of actuators as compared to the previous one.
Yes, it is having lesser number, but any guess whether 6?
Yeah, it will be around 6 or 7,
Yeah.
according to.
Okay. So the interesting part is I will run this video again, and I would like to emphasize that it is not having any actuator at all. It is walking down the gravity, and you can actually create something, a structure which can, without motor, walk naturally down the gravity. And if we can do this, can we try to adapt some of the principle of dynamic walking, the way we get into, say, natural rhythm and keep on walking with minimal energy and create today's modern machine? That's where there is a lot of effort and work which is being done in today's world. Can we create energy efficient robot which can tackle challenging environment? So considering having this background, I thought let me now get into the main topic, which is robotic process automation and quality enhancement. And me being roboticist, I'll see as if we try to use robots for automation, it will automatically lead to quality enhancement, and that's what I would be focusing in today's talk. And I would again like to reiterate that this topic is very important as major industries across globe are moving towards intelligent, adaptive and data-driven manufacturing. And if you would like to compete China, then this is very important that we use robots for process automation and quality assurance, as we are much behind what they have achieved, kind of factories that they have. And you'll also get some idea as I move ahead in the second part of the presentation. So let me give you some statistics. As far as automation market is concerned, it is expected to grow significantly in time to come, and it is projected that by 2032, the market would be worth 600 billion US dollar. In addition to that, AI will also penetrate significantly in the area of manufacturing, and its usage will increase 5 times what we are having today. And this is the number given. However, I suspect that it could be 10 times what is being used today. And there would be significant role of AI, data-driven manufacturing in time to come. And hence, with this increase in automation and AI manufacturing, we need strong research and curriculum in this area. And I assume that's what has also motivated this FDP, where if it may ignite you to work, take up some of these areas, will eventually also help in nation building. As far as robotics is concerned, I would like to emphasize that today there are approximately 4 million robots worldwide, and there are 6 lakhs annual installations are being done. And this majorly Asia played important role in this global deployment, and there is going to be total annual growth rate of the order of 12 to 15% in time to come. When I say robotics, robotics is all kind of robots, industrial robot as well as service robotics. And I would like to give you this image, which essentially focus on industrial robots, which are being increasingly used in manufacturing application for handling, assembling and deassembling, welding, soldering, clean room, dispensing, processing, and others. And it is projected that today we are in 2025, and by 2033, the market will grow by 163 US 163.9 billion US dollar, and it is expected that market will grow with CAGR of 11.5. So here we are majorly referring to industrial robots, which are increasingly used in manufacturing industries. And I would like to give you another interesting fact. So this diagram was published by International Federation of Robotics. And on x-axis, you can see that robot installed per 10,000 employees in manufacturing industry in 2023. And if you look at this figure, then in South Korea, Republic of Korea, there are 1,000 robots per 10,000 employee. On the other hand, Singapore is next to Republic of Korea, which is 717. China, 470 robots per 10,000 employee. And then Germany and then Japan is 419. So top 5, if you look at countries, out of top 5, 4 are Asian countries. You may say, sir, where is India? But before I take you to India, I would also like to give you the world average, which is 162. So the world average is 162 robots per 10,000 employee, and Indian average is 11. So when we talk about nation building, Make in India, this is going to play important role. This number is significant, and this is also an opportunity for people like us who have been working in the area of manufacturing, robotics, automation, where we see that there is significant opportunity where automation, robotics, and quality assurance, we need to develop interesting curriculum, workforce in the form of student, which will participate in industrial growth in time to come, because this number in time to come will significantly increase in India. So a fundamental question comes to our mind: why robotics matter in automation at all? And why should we use it? So obviously humans have limitation, and our work capability is also very subjective. It all depends on what kind of mood we are in, with whom we have fought yesterday, and that may also reflect on quality of product that I'll create. On the other hand, robots are very objective, and it delivers precision which human cannot match. Full stop. So that's something which human cannot. And if we talk about accuracy with kind of actuator and sensors that we have today, robot can easily achieve accuracy of micron level. Another interesting part is it can be used for 24/7 operation, and our subjectivity of human will also hamper the consistency. Perhaps the component that I may create today may not be the same as what I create 10 days after today. On the other hand, robot can consistently create component of same quality day after day without tiring. That's what is being meant by consistency. And they're also highly flexible. I may use robot for lathe machine has certain usage, and it is meant to be used, or drilling machine or milling machine has certain usage. As far as robot is concerned, it can be used for drilling, it can be used for milling, it can be used for assembly operation, it can be used for pick and place operation, it can be used for spray painting, welding, and it has high flexibility. And it has capability to incorporate data-driven AI-based decision making inherently into it, because it is highly programmable in nature. So in summary, all these features of robot reducing to reduction in defects and increase in quality throughput. So if I compare or summarize the process impact, if I use manual intervention and robotic, then we can say that robot can outperform in terms of speed. They are much faster. They work objectively, highly scalable, and the error rate that they may generate are also significantly lower. And that's one of the reasons where robots should be used in automation. And in subsequent slide, I'll show that when you use robot in automation, the quality assurance is inbuilt. It significantly improves the quality of product. Rather than seeing robot as quality inspector, we are seeing that robot is contributing in increasing overall quality of the product. I would also like to touch upon Industry 4.5.0 revolution. Professor Kaushal must have mentioned about Industry 4.0 in his first talk, and he must have given very nice journey from Industry 1.0 to 5.0. I'll talk about Industry 5.0, which talks about collaborating with human, which essentially would lead to sustainable manipulability. So it will try to take away some of the limitation of Industry 4.0, which is machine heavy. On the other hand, Industry 5.0 talks about sustainable manufacturing, where robots will collaborate with human, will take AI-powered decision, and will take away some of the tasks which are repetitive, cumbersome, where human subjectivity will increasingly affect the accuracy, quality, and hazardous tasks. In fact, it will amplify the creativity of human, because human is creative inherently, and autonomy, which is achieved AI-powered decision, will amplify humans' creativity. Important issue to be addressed is real-time human-machine interaction, where a lot of research work which is being done, and eventually we would be having sustainable manufacturing. And Industry 5.0 says robot will not replace human, but collaborate with them and increase productivity. I would also like to emphasize some of the key technology which will play a very important role in Industry 5.0 in general and automation with help of robots and subsequent quality assurance. And these technologies are LiDARs and 3D vision, Internet of Things, edge computing, generative AI, digital twin, and predictive analysis. Moving forward, at this juncture, I would like to emphasize, we have seen a gamut of robots in applications of robot. However, I would like to emphasize on these three robots which are going to be increasingly used in industrial environment in time to come, where we'll have industrial robot, the robots that you've seen in assembly line of an automobile industries, which are being used for pick and place operation, welding, painting. So this robot will get embedded with emergence of Industry 5.0 and knowing the fact that now robots are not meant to be kept in cages, they'll be working along with humans, they'll be collaborating with human, and we need to create environment which is safe for human robot collaborative work. And second category of robot would be collaborative robot. In addition to that, there will be a lot of mobile robot, which could be wheel robot, legged robots, automatic guided vehicle, which would be used in shop floor increasingly and which would give mobility, logistic advantage, and enable material flow. So these are the three kinds of robot primarily going to play a very important role in time to come as far as industrial automation is concerned. Now, it is not only robot, but there is also very popular notion which is known as robotic process automation. Now, robotic process automation uses a robotic agent. So it is not a real hardware, but it is a robotic agent which follows set of rules which are given by input data, and it performs automated testing and quality assurance. It ensures paperless workflow, and you can approve various uh, uh, things in much faster manner with zero manual error. And this robotic process automation can lead to scalability, flexibility, accuracy, quality, productivity, and efficiency. It allows you to perform advanced analytics. It enhances security and also result into cost saving. So the physical robot with this robotic process automation, which is nothing but software automation, is nothing but founding leg of end-to-end smart factories. And hence they need not to be seen separately. When I say robots, robots are always combined with robotic process automation, where there is a software agent or a robotic agent which is doing this task, and combined effect will significantly increase productivity, reduce cost, and also improve the quality. So with this foundation, I would like to take back to the main theme of this talk, which is process automation. So if we try to understand process automation, it essentially tries to achieve automation by encouraging machines and software with minimal human intervention. And process automation leads to significant productivity, safety, and quality. And as I have been repeatedly telling, that it is key to smart manufacturing that we are trying to see today, getting implemented in even Indian scenario. On the other hand, we have seen some of the capability of robot where robots are consistent performer, do tasks repeatedly and create product of similar accuracy day after day. So high accuracy, repeatability. It can handle repetitive tasks and avoid subjectivity of human error and reduce human fatigue, and it enhances workspace safety. So when I do process automation using robots, it eventually lead to quality assurance, and outcome would be significant improvement in dimensional accuracy, uniform product appearance, lower defect and rejection rates, and higher customer satisfaction. And hence, what I would like to emphasize being roboticist is robots build quality directly into process rather than just inspecting it at the end. So let's not see robot as a quality inspector. We'll also have one slide where we talk about it, but rather I as a robotist would like to emphasize that process automation through robots will lead to automatic quality assurance. And that's something very important to look into. And this aspect is not only limited to industrial environment. In tomorrow's world, it will get applied in agricultural industries. It may get applied in service industries, inspection, surveillance, and many other spaces. So fundamental questions arise is that how robots improve quality. So obviously these are the two important pillars of robots, the one being sensing, precision, and AI with the help of state-of-the-art sensors such as machine vision sensor for perception. It also uses force, torque, tactile sensing, and it also uses haptics, sense of touch, and AI-based tools, techniques to further improve the decision making or classification of defects. Lot of sensing decisions are also being taken with help of AI based on the measured information. So that's one very important part, and that's why I also discuss attributes of robot, because in robot sensing plays very important role. And we talk about thinking. So thinking part is attached to intelligent control. So it is closed loop control, real time monitoring and data driven decision, which makes action so precise, which leads to repeatability, accuracy, and eventually it leads to quality. And that's how robot improve the quality. Nevertheless, there are also robot-based quality assurance technology, and I would not like to limit myself to these technologies. However, there are technologies where automated inspection, as it is being shown in this figure with help of vision sensor, can be done. One can get the measurement, send it back to AI-based algorithm, and it can perform defect detection in better manner based on the data received. It can also have a digital twins which might have software replica of robot. So this data will be applied to software replica and then it will perform predictive analysis. And one such example is nothing but automotive plants using machine vision for detecting various defects. And I assume that Professor Desai must have also mentioned about vision-based defect detection in his presentation. So moving forward, I am reaching for summarization of the second part in next 2-3 slides. So I see robot as a quality gatekeepers because it has ability to inspect 100% of product, because if you rely on human, it may so happen that depending on the subjectivity, I may miss some products to be inspected. I may oversee some aspect, but robot will not. Considering the sensing and actuation capability, it will also serve as precision executor and it will have nanometer accuracy. It will build on a lot of data. It is a data collector. You can always go back to data and then make decision based on this data. It will keep log of this data and which should be very valuable for improving accuracy. Robot will also learn based on this data, various task operation. It is also risk eliminator because it can work in hazardous and emergency scenario, handle dangerous material, hot material, risky material, isn't it? And it is also consistency guardian, which will keep on creating same part day after day objectively and certainly overperform human in that context. And it will also be speed enabler, which will work 24/7 operation, and eventually all these things will have quality impact. And it is shown in this link that it will significantly reduce the defect and it will make it less than 0.1%. It would increase the yield by 20 to 45%. It will perform significant cost reduction. It will reduce the waste and it will also reduce rework significantly. That's also a very important part. And hence, it will have a lot of impact on quality assurance as a whole when we combine robot with automation. So I would like to summarize this as robot transform quality by increasing precision, as we have discussed throughout, by eliminating variation and ensuring consistency. It can perform repetitive tasks so that we can automate these repetitive tasks. We can take care of hazardous and high risk tasks and do it with same accuracy and precision, which human may not be able to do. As it builds on data, all decisions are data driven, so it also provides traceability. And that's very important aspect when we use robot and combine that with sensing and data driven decision. And one of the important part is it is highly scalable, intelligent, predictable, and it is very well suited for Industry 5.0 and smart manufacturing. And again, I would like to emphasize that it is robot with RPA, which is going to play important role. So it is physical robot with software robotic agent is nothing but future of quality engineering. And I'll also try to float some of the thought process and ideas which can be playing very important role for future of quality automation. So we'll have self-learning robot. So based on the data and today's AI advancement and machine learning, it will learn on its own and keep on improving its capability. And that's what is going to be very important in time to come, and a lot of research are being done. It will also build on Internet of Things, sensing and real-time alerts, and it may also perform predictive maintenance on its own. It will also ensure lights out. This was very popular for Philips plant, where there were all robots in the factory, and then factory can run 24/7 as everything is being done autonomously. You don't need any lights in the factory, and it can keep on working and keep on. There are no humans, no lights. That's how this word was, light out factory, came into picture. Digital twins is also very important part, where there is a simulation running parallelly and it is predicting the future. And based on the predicted future, the actual physical hardware is taking decision, modifying its decision. And with all this, we may be able to create space-based reliability for extreme environments, as I would also be talking about space robot in the third part of my presentation. So I would like to emphasize that quality is not inspected in. It is not that we are inspecting. We need to go beyond that. We need to build in quality through intelligent automation with help of robots. And that's what is very important and going to play important role in time to come. So I would like to conclude my presentation with the second part of my presentation with some key takeaways for teachers. So I would like to emphasize that now we are no more in a world where we are having static system. There is a drastic shift change from static system. We are having intelligent autonomous system, and we need to integrate control, AI, sensor towards achieving intelligent, adaptable, and smart manufacturing. And obviously, automation enhances quality and productivity, and there is a need of precision, repeatability, and reliability. Now, in order to achieve this, we need interdisciplinary breadth, where we need to have know-how of mathematics, mechanics, such as kinematics, optimization, control system, which is PID, MPC, model predictive control. AI ML will also play important role, not only in defect classification, but lot of robotic algorithms. Today, in time to come, when we talk about robot which can learn on its own, so basic algorithm framework will also be based on AI ML. And mechatronics in the form of sensing, actuator, and embedded hardware will play important role. And hence, considering these two aspects, it is increasingly going to play important role in evolving education system in time to come. And there is possibility of getting a lot of interesting project, research input in these areas. And there's also need of preparing students for such taking such challenges and tasks so that they would be industry ready for smart factory environments. So there's a need of precision, capability, there is a need of interdisciplinary breadth, and as a teacher, we need to put in a lot of effort to bring in this and helping tomorrow's students to get this skill set, know-how, as far as student projects are concerned, there can be a lot of interesting projects can be thought of here. Just I mentioned 2-3 projects where one can design vision-based inspection system, lot of analysis can be done, pick and place with defect detection, digital twin-based simulation, and then taking decision on real hardware subsequently. There are also interesting research challenges, such as robust control under uncertainty. You must have seen that the big dog was being pushed in when we talk about Boston Dynamic robot, and that disturbance it was able to take. So those kind of uncertainty it needs to take into account. It may so happen that the system itself is so complex enough, model is not fully aware. So we may also need to use data to predict this uncertainty and come up with a learning-based robust controller, or it can be stochastic controller, learning-based automation, low-cost vision system, human-machine, human-robot interaction is also going to play an important role as we refer to it in Industry 5.0. Finally, I would like to conclude that process automation enhances efficiency and quality, and there is strong role for teachers in shaping future workforce. And I'm sure many of you will take up these challenges in time to come and make a lot of contribution and also create student know-how in this area. So this was the second part of my presentation, where I wanted to emphasize that as a roboticist, we would like to build in quality inbuilt into the process rather than seeing just as inspection, robots being used for inspection. Now, I would like to show a case study where certainly this case study is towards achieving autonomy, and this also a robot. So I would be referring to space robotics for doing all operation in autonomous manner. I'll try to talk about some research challenges, and eventually it will lead to quality operation, zero failure operation. And that's where this case study focuses on. So indirectly, it emphasizes autonomy, usage of robot, and eventual output would nothing but quality assurance in a way, a repetitive task that one would be able to do it. So as I've been doing research in the area of space robot, I thought of highlighting some of the challenges that space faces. And the video that you may see is of image that you see is of Chandrayaan 3, and we have Pragyan rover, which is also a robot, and an entire operation was being done. It has a lot of autonomy, inbuilt autonomy, as well as that it was teleoperated, control. So it is combination of semi-autonomous operation. Nevertheless, autonomy play a very important role in this mission. And you must appreciate why I'm talking about space, because there is a round of testing which was being done to ensure that whatever they make is quality, and then it will last until last stage of its mission. So as far as space is concerned, we have extreme environment testing, we have vacuum, radiation, extreme temperature. We obviously do simulation before deployment. A lot of simulation needs to be done, and robots need to do autonomous fault recovery, no human intervention. We need to have 99.99% reliability, and mission would be of 5+ years, because these missions are very costly and longevity of missions are very important, and hence quality of everything, whether it is algorithm, it is software, whether it is hardware, sensor, the robotic system, the entire RPA plus robotic system. And robot should have self-diagnostic ability and healing ability and remote operation. So in nutshell, I would say that it would require zero failure system mandate. Autonomy and quality assurance are key in space, and space robotics had significant role to play. And that's what I'll try to Very briefly discuss because there is a lot of research work which may be mathematically involved. So I'll just touch upon because we have around 15 minutes to go. And I would also like to keep 5 minutes for question answer. So I'll very quickly give you some of the space robotics which are being used in space. Canadarm1 was operational from 1981 to 2011. You will be surprised to know it was 15-meter long and 400 kg robotic arm. Then Canadarm2 is at present operational on International Space Station, and it is even longer, 17 centimeter long and 800 kg long. And then there is also 14 degree of freedom arm Dexter, which is 3.5 meter long and 1600 kg weight. You may be glad to know that ISRO is also planning a space station where there will be a lot of robotic activity which will happen in time to come. Even there were some robotic activities which are being done by Japanese space agency JAXA and NASA in past. So these are some of the evidences of robots usage in space, and my research work essentially focuses on on-orbit services, which is nothing but usage of satellite-mounted robotic system for inspection of space station satellites, repair, refurbishment, refueling, construction in space, capture, orbiting of objects and debris. And obviously the important thing here is autonomy, usage of robot and quality assurance. Well, when I say quality assurance, I would like to design algorithm in such a manner so that task is being done with zero failure. And here is example of some of such operation where you can see that the antenna is being fixed in space with help of space robot. You can see robots are refueling the orbiting satellites. Yes, here you can see that autonomous assembly of antenna, because anything outside satellite, it's very important that things are being done with help of robot with utmost precision. And I at IIT Jodhpur, I work on reactionless manipulation, dynamic identification, capture and post-capture control of space robot. We have also developed port-based space robot, and then we also work on vision-based control of space robot. So I'll very briefly take you, I'll take up one problem of capture of orbiting object by space robot. This is very challenging problem and very important because there are more than 3,000 active satellites in space, and there are more than 31,000 debris of size 10 centimeter or more, and 70 of track objects are debris. So 70% of track objects are debris, and these debris can destroy an operational satellite. So it's very important to mitigate this debris by some mean, and what we are focusing on is satellite mounted robotic system. So you can see that there is satellite mounted robotic system which is mitigating a debris, which can be non-functional satellite which need to be either sent back to Earth or in graveyard orbit. And there are major three operations. In first phase, satellite mounted robotic system approaches the target. Then there would be capture phase where there would be impact and capture. So we need to ensure that there's a stable contact. And then there would be post capture maneuvers. Now in space, these satellites are free floating. And there would be non-holonomic constraints if the satellites are thrusters are being shut off. So the satellites would be free floating, and this would bring in a lot of challenges, and these challenges we are trying to solve as a part of our research at IIT Jodhpur. So first part is we focus on reactionless manipulation. So idea is very simple. You can see an image where there is a green square box which is imitating satellite, and there are two dual arms which are being shown with green color and blue color. And what you may see that if thrusters are being shut off, then any movement of arms will result into change in the orientation of satellite. Now that may require replanning. We need to mitigate this attitude disturbance. We may also require to minimize impact when these arms are capturing a target, and we may also require to take into account various constraints in the form of similarities, obstacle avoidance. And we have come up with very interesting approach where planning based approach is being employed, where we try to plan motion of robot backward, where given and velocities are being imposed, and then we try to perform control in the forward direction. So you come up with interesting path planning based strategy and time scaling approach. I'll not get into detail, but this video shows final uh, motion of the robot, which successfully shows that it could reach the desired grapple point with the given velocity. In second part of video, there is an obstacle which is being introduced, and it can be seen that the robot moves to the desired grapple point with required velocity. Required velocity is also very important because we need to minimize the impact, and here there is a spatial robotic system where we are shown that it is able to plan the motion of robot by minimizing attitude disturbance, ensuring that robot reaches the point in fixed time window, and it also satisfies the constraint. Oh, I think I'm sorry, I think this slide has come up here. Perhaps it was supposed to come first time. So another important thing is when we try to capture unknown target, there is a problem as far as post-impact stabilization is concerned. There's also closed loop constraint, and then what may happen that when you try to capture the tumbling orbiting object with dual arm, the satellite may get reoriented if it is not being controlled, if it is free floating, and it may change its attitude. So idea is can this entire operation post impact control in such a manner so that the satellite mounted robotic system perform this operation in reactionless manner. So here what you may see that robotic operation is being performed where object is tumbling, and then the object is being docked onto the satellite, and this entire operation is being done in such a manner so that the satellite attitude does not get disturbed. All constraints are being enforced, singularities are being avoided, and task was being successfully done. We have also been working on very interesting dynamic identification techniques where we do not try to rely on low signal to noise ratio, because acceleration and torque signals are low signal to noise ratio. So we also come up with an interesting approach where we try to perform dynamic identification, where we try to get mass inertia property of a robot which is already being assembled, because you may require to update this mass and inertia property in real time because fuel is getting consumed. The friction and damping parameter gets changed, and in real time without disassembling robot you need to come up with identification so that you can improve your control performance. And we have come up with very interesting velocity momentum based approach for dynamic identification, which we publish in AIA JGCD. We also done data driven predictive control. In many times it may so happen that many control strategy that you employ, it relies on the dynamic parameter that you have or model parameter that you have. Nevertheless, it may be very challenging to precisely estimate joint friction and disturbance. And we have come up with very interesting data-driven control strategy which uses stochastic control. And we have shown that for different friction model, root mean square error based on our algorithm, which is sparse Gaussian process based stochastic probability control and MPC. So our approach is performing significantly better for different friction model, different disturbance, and different base to link mass ratio. And this was one of the important contributions that we have done. We also worked on vision-based control where idea is very simple. So I'll run a video where you can see a red image with 4 points. There's a blue image with 4 points. And idea is to move camera in such a manner so that blue image matches with the red image. And I'll run this video and you will see that I'll move camera in such a manner so that blue image matches with the red image. And this is known as image-based visual servoing. So if I try to imitate this for a robot, so robot would be having camera, and I need to move this camera in such a manner so that my current image matches with the desired image. And my desired image is I would want to see this car the way it is being shown in the second desired image. And how will I move camera? I move camera with help of my joints. So idea is I try to move the robot in such a manner so that I see the desired image, and that is known as visual servoing. Now this visual servoing would be very useful in teleoperation. Very useful to replace teleoperation. In performing various proximity operation, autonomy will also play important role. And this visual servoing would be very good substitute of teleoperation where you can perform operation in autonomous manner. And research idea that we were having is, can we do visual servoing in such a manner so that the attitude disturbance are minimized as far as possible? And we came up with very interesting algorithm where I'll just run the simulation where you can see that there is a dual arm robotic system where it is moving in such a manner so that error in image space is getting reduced, where blue image is getting converged to the red image. In addition to that, we are also ensuring that a lot of constraints which are being adhered to while we are performing this operation. I'll not get into much of this detail, but we also done some interesting work where we have done path planning in image space, and we have also embedded a lot of constraints such as joint limit, collision, singularity, and we have improved the performance of our algorithm where again you can see that visual servoing is visual servoing is being done successfully. We are also trying to avoid singularity and we are going to minimize base reaction. So idea here was to come up with path planning based approach in image space which perform visual servoing with singularity avoidance and minimization of base reaction. In addition to that, we also came up with visual servoing to tumbling object for debris capture, and I'll just move to the video where you can see that our approach, the current image converts the desired image easily. If you can see this, in the classical visual servoing, as object is rotating, current image, blue image is not converging to red image. However, in our approach, current image is easily converging to desired image. And here you can see that there's a camera which is moving in such a manner so that current image is converging to the desired image and eventually the feature error is getting down to 0. So camera is servoing to the moving object in such a manner so that we are getting the desired image. And here is the demonstration where you can see that object is tumbling and robot is servoing to the tumbling object. We have been also working on developing microgravity experiments where there are various approaches that can be used. For example, we can use air-bearing testbed, which may be good for planar studies, and I'll talk about this air-bearing testbed in next 2 slides. We can also have hardware-in-loop systems. I'll also touch upon hardware-in-loop systems, so I'll not get into much detail here. We can have neutral buoyancy. However, it suffers from water-induced drag forces. We can have parabolic flight, which may suffers from short flight time duration, reduced gravity condition. We can have free fall, that also suffers from short time duration. We can have force compensation. However, microgravity cannot be mimicked with help of force compensation completely. So we focused on 2 aspects. One is air-bearing testbed to mimic the space scenario and hardware-in-loop simulation. So which I'll very briefly touch upon, and I will be concluding my presentation in next 2 slides. So first image shows air bearing which is being placed just below this setup, which is shown in the third image. So this blue color air bearing is nothing but porous air bearings. So there is a carbon dioxide cylinder, pressure regulator and distributor. And from distributor, air will pass through these air bearings. And then this air bearing will create pressure and it will lift the object. And here what you may see that we are mimicking a satellite, where you can see that a free floating scenario was envisaged with help of this setup, where the object here is mimicking a satellite and there are air bearings, and we can create this free floating scenario with help of this air bearing test bed. So this can help very well in mimicking planar scenario. We also include embedded hardware, sensors, actuator, and you can see that there is a robot which is integrated, so dual arm, where obviously after some time the setup is drifting, so one has to be careful, and it requires a clean room, dust-free environment, highly finished granite table. However, we could demonstrate here that we could create a setup, we could do some meaningful experiments. We have been working with URL Satellite Center, ISRO, where we have been working on hardware in loop simulator. So I'll briefly talk about what is hardware in loop simulator with help of this image. So in this image, there are 2 robots. One robot is carrying a debris, and another robot is carrying a satellite mounted robotic, so one robot is mimicking satellite mounted robotic system, other robot is carrying an object, and there is a simulator which is actually mimicking actual outer space scenario, and the output of simulator, which is nothing but states which are going to this hardware setup. And this hardware setup will play important role in giving us idea about the impact forces, because these are very difficult to estimate, and these are being fed back.
online.
These are being
না
these are being
দোকান
fed back, and
কলেজের জন্য দুটো আইসি
Yeah.
অর্ডার করতে হয়েছিল, এরম চিপ, এরম দুটো দুটো চিপ অর্ডার করলাম। দিয়ে এই তো 5 তারিখে
I think
করেছিলাম,
your
আর আজ
mic is
কালকে
I
এসছে,
think I
কালকে
don't know who
দুপুরে
is
এসছে
speaking, but
অর্ডারটা।
your mic is on.
কালকে কলেজ
Can
যাইনি
you
তাই আনিনি,
switch
আজকে
off your
গেলাম
mic?
দিনই এলো।
Yeah. Just Rohit Kundu, are you there? Just unmute.
Yes, sir.
Yeah. Just unmute.
Yes. So with this,
Yeah,
so this is the idea of hardening.
such an interesting topic is going on, and people should be very careful to keep their
No,
minds
it's okay. I
mute.
think we are now, say, in today's
Yeah.
world, we have become prone to everything. And kind of uncertainty that we are living in, it has made us more humble, Professor Dan. So don't worry. We are now, we have learned how to be more humble and then more. So
Yes, of course, of course.
yes, I hope you got the message what I'm trying to convey, but then
Oh,
anyway.
of course.
Yes. So and so I just, this is last slide of my presentation. So we have also contributed in Gaganyaan mission, where we had collaborated with Inertial System Unit ISRO. So in time to come, we'll have this Gaganyaan mission where we'll have first human flight to space. And initial round of this flight will have robot going to this flight, and the robot name is Vyomitra. So we have collaborated with ISRO, and then we have developed some interesting algorithm, vision-based control, and we also done some zero gravity dynamic studies, joint offset calibration, dynamic identification, visual servoing, motion planning, reactionless manipulation. And with this, we also work in the area of cooperative manipulation, where you can see that there are multi-mobile manipulator system moving in dynamic environment in the first video. So we work on cooperative manipulation, multi-mobile robot system. We come up with very interesting set of algorithm for segregation, which are resilient to perturbation and go to the desired configuration. In past, we also work on um, whole body motion planning of humanoid for obstacle avoidance and uh, we have developed some interesting algorithm for force control of compliant robot, and we also developed, this is very close to my heart. You can see a robot very smoothly moving stairs, and this is one of its kind. At that point of time in world, we had a lot of interesting research work done out of this work, and you can see that robot very nicely researched out and designed and moving stairs very easily. And this is the standalone version where it is climbing stairs very smoothly, where you don't need any bulky setup. A very cheap robot can be used for surveillance. We have also developed a dynamic simulator, which is freely available. If you are interested, you can actually look at this recursive dynamic simulator ADSIM, which has lot of simulation, lot of examples which you can use for your research, develop your own trajectories, control algorithm. And we have also done a lot of end user centric technology development. So in first video, we were working with medical industries where aims Jodhpur, and there was some project where we were trying to work on teledentistry, and then second work is some demonstration. So it is demonstration of some of the work that we have done for Yomitra half humanoid. We are also working with Jory Digital Industries, developing algorithm for robotic therapy, where a laser-based therapeutic device will be attached at the end of the robot. Another interesting work that we have done with TVS Motor as a part of 5-year project that we were having at IIT Jodhpur. So here you can see that there's a self-balancing two-wheeler, which was, so they gave us a moped and then we designed entire control moment gyro. They manufactured it for us, and then you can see that some perturbations are being given by the student, and moped is actually balancing on its own. And we have also built this autonomous guided vehicle we have designed it and built by TVS Motor for them, which they have taken back from us. So with this, we also have some in-house developed research platform, parallel robot, space robotic platform. We also assemble quadcopter, quadruped. We have been doing some interesting work on quadruped reinforcement learning based approach, and then this is we were working on whole body motion planning of humanoid, and this is some hardware. This is some facility that we have at robotics lab at IIT Jodhpur, and we also augmented. So with this, I think I respecting the time, I would like to thank many students and faculty collaborators who has work, and I would also like to emphasize IIT Jodhpur offers MTech in robotics. So if you are interested to pursue higher studies, I'll take this liberty to. Last year we moved from robotics and mobility system to robotics, and I would like to thank you for giving this opportunity and share some of the thought and work that is being done by us. And thank you. I would like to give my personal thank to Professor Dan. It was really wonderful that you could come to IIT Jodhpur, help us in design of our entrepreneurship curriculum. It was really nice time when you were here. Thank you. Thanks a lot.
Thank you, Professor Shah. Let me tell you, I mean, see, this robotics is an area. Professor Puntu, try to mute someone who is speaking. So, is robotics always a very interesting area, very, I would say, exciting area, and which is an inseparable component in the
Yes, Professor Dan, I think I have lost your voice. You are muted.
mute me. Yeah. So I said that robotics is always very important, and particularly for industry 4.0, manufacturing industry 4.0, robotics and robots are inseparable, absolutely inseparable in industry 4.0. And last but not the least, I mean, I feel so proud that we are having a speaker today who actually is working for a national cause, that is a ISRO project, and he's a top scientist in the field, top engineer in the field. And Professor Shah, really, I mean, I remember our discussions at IIT Jodhpur and all, and now I congratulate especially for this recent achievement that
Thank you.
and that is wonderful. Sometime we will have a detailed discussion on that, but
Sure.
thank you very much. It is already 9:15, so I
Yes.
would not I would not expect that there will be many questions from the participants, but maybe some will be in the chat box or whatever, and maybe if that is required we'll pass back, because now there is
Sure.
not much time to discuss here. So I would request, with your permission, to hand over the session to Professor Rai, who would conclude.
Sure, sir. I think
Thank you once again,
for
Professor Shah.
thank you for invitation. I would have come in person. Maybe next time we'll see whether I can
Please
invite
do,
you or I
please
can be
do.
there
We would
in
love it.
person.
We would
Yeah.
love it. Yeah, we would love
Wonderful.
to host you. Yeah, sure,
Sure.
sure, sure.
Sure. Thank you.
So thank you. It is a lovely presentation, very nice presentation. I really enjoyed, and it will be beneficial to our participants. So already our Professor Dans already has told, so nothing to say. So it is very nice and wonderful. I think all the participants have enjoyed. So thank you very much.
Thank you. Thank you. Have a good night.
Good night.
Thank
Good
you.
night.
Good
Thank
night.
you.
Good night,
Good
Professor
Good
Shah.
night. Good night. I'm leaving the meeting. Can I leave the meeting?
Oh, yes, yeah,
Yeah,
oh, yes, by all means.
yes,
Please,
yes,
please.
yes, yes, yes.
Sorry to hold you in your dinner time. Sorry.
Okay, thank you everyone. Please, before leaving, submit the feedback link that I have shared in the chat box. Before leaving, everyone, please fill up the feedback form that I have given in the chat box. Thank you very much.